Hello and welcome to our series of lectures on the topic of regression. Over the past few lectures, we've discussed the idea, we've motivated the use of this approach called regression, and in the last lecture, we've even looked at the idea of deriving the ordinary least squares regression, and we did that in the simple linear regression case. Today we're going to look at how you can implement a regression in through software, and we will show it to you in both Excel as well as Matlab. But the important thing is to just understand the core concept and the terms, so tomorrow you would be able to implement it with any software of your choosing. Now, with respect to the main topic that we discussed last time, which was simple regression. So when we did this whole analysis on the derivation for the ordinary least squares, we took a case of simple regression, which just means that there is one input variable that is involved. Today we're going to extend that. We're going to look at the case where there are multiple input variables. So let's start by setting up an example, and I will show you a demonstration in Excel for performing the multiple regression, and we can talk about some terms that you might encounter when using this software. Okay, so this is a sample data set, and what you have in column A is they're just serial numbers to give you an idea of how many data points there are, and I've chosen an example where there are 88 data points. The variables B, C, D, and E, as you can see selected on the monitor, are actually the input variables, and column F, which is shown with which is highlighted and also labeled as Y, is your output variable. And so for the first time, you're interested in creating an equation, a regression equation that maps these input variables to Y, the output variable. Okay, so the way you would do that, and I'm using Microsoft Excel out here, would be to go to you see the topics on top that say File, Home, Insert, Page Layout, where my mouse is, and in that you'll select Data. So usually your screen might be at Home. You would go click on Data, and then you would go to Data Analysis, click on that, and that will pop up a set of possible tools that you could use, analysis tools. And for some versions of Excel, you might not have this readily. That is, you will not have this data analysis button already, and there you usually need to go and add it in, and it's called an add-in, and it will be there. It's there in the software, but it's just not installed for you. So here you would choose the topic regression, and you would click on OK. And now it's asking you to tell it where the data is. So that's what I'm going to do. I'm going to show it where the data is, and the way I did that was to kind of select that whole column. And if you're vaguely familiar with Excel, you can just use some hotkeys to do that as well. Just note that I'm also selecting the titles of the variables when I'm inputting the variables, and because I do that, I need to check this box that says labels, meaning that I've also provided you with labels. The idea here is the constant is 0 basically means should the regression line be forced to go through the origin, and we don't want that, so we won't check that. That basically means in your equation y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on, your beta naught is going to be forcefully set to 0, and that's not something you want. The second also gives you, out here you have something called confidence level, and that gives you the option of choosing a confidence level, or essentially an alpha that is different from 0.05 or 95%, but we're quite happy with 95%, so we will leave that. There's a couple of other options. The thing is, I said I want my results in a new worksheet, so that's what I'm going to select. So I say OK, and this is the output that I get. You might notice that it's put into a new sheet. So let's just look at this output and try to process this. So what it says out here is that the important things for you to note is the R squared. The R squared is in some sense a measure of how good your overall fit is. Essentially, it tries to say how much of your variation in Y is actually being explained by the model that you've created versus how much of the variation in Y is just pure noise. So the R square is essentially a number that goes from 0 to 1 and is essentially the square of the what is called the multiple R. Okay. There's another term called adjusted R square. It's a very important term, and we'll come to that in a minute. And you finally have standard error out here, which has been highlighted. And standard error is nothing but for a given predicted point, how much is the general deviation of the actual point from the fitted model on average. So that's what is being captured in standard error. Okay, so and observations is just the number of observations there are. Okay, below this top table that we've just discussed, you see two tables. Let me first talk to you about the bottommost table, and then I'll come to the table above. The idea here is that here you have the intercept and the 4 input variables. Now, what is called as the coefficients correspond to the betas. So when it says intercept, the coefficient 9.29 essentially talks about beta naught, and correspondingly for A, B, C, and D, their respective betas, because just remember that we have a functional form of the nature, and I'm just going to type it out here, y is equal to some constant, let's call that beta naught, plus beta, let's call it 1 times A, plus beta 2 times B, and so on. That's the functional form that we have, and it goes all the way from C and D. The big question is, what is beta naught, beta 1, beta 2, and that is what these coefficients represents. You can call them beta A times A if you want, but essentially the coefficient corresponding to A is what we're talking about here. And these are the coefficients, these actual values that you see here. Excel has done this regression for you, and it gives you these results. The standard error that's being discussed here is the standard error around this coefficient, right? So this coefficient is nothing but an estimate based off of a sample, going back to our topics in inferential statistics, and the standard error pertains to the uncertainty or the standard deviation, quantifying it with standard deviations. The uncertainty around that coefficient, which is being quantified by the standard deviation associated with this estimate, because this is an estimate and there's some uncertainty around an estimate. Just like you had a sample mean, and the sample mean which you got from the data, which is supposed to represent the population, the sample mean essentially is a random sample from a distribution, right? Because each time you take a sample and you take a mean, you're not going to get the exact same value. So you're getting a value from a distribution, and that distribution has some standard deviation, right? We, for instance, earlier discussed about this. The standard deviation of the sample mean is something that you can get from that distribution. So similarly, the standard error quantifies the uncertainty around this coefficient, around each of their respective coefficients, and it does so through the measure of a standard deviation. Great. So now finally, from standard error, we go to the t-statistic, and the reason for that is that this estimate, which is this coefficient, the distribution associated with this estimate, just like the distribution associated with the sample mean was t-distributed if you did not know the standard deviation of the population. That's the same core idea here, which is that it's t-distributed, and Excel calculates this t-statistic for you and gives you the p-value associated with the t-statistic. Okay, and what you have out here are a set of p-values, and what they represent is that they represent these p-values and these t-statistics correspond to the hypothesis that this coefficient. So let's take one example. So I'm just going to highlight this example. So we've got some coefficient for A. and that's 0.2420. Okay, what we then choose to do is test the null hypothesis that this coefficient is statistically different from 0, and this p-value is the probability that comes about as a result of performing this hypothesis test. And as you already know, the p-value is nothing but the probability of seeing this data if the null hypothesis is true. So if the null hypothesis that the sample coefficient is equal to 0 is true, then the probability of seeing the data that we've seen is this value, which is 5.21 times 10 to the power 17. Now that's a very low number, right? That's a very, very, very low probability. And so the idea would be that out here we would reject the null hypothesis that this coefficient is statistically no different from 0. So if you take a look at this, all of these p-values at least are fairly low. This sign 5.21 e power minus 17 just means times 10 to the power minus 17, which means it's a very low number. And the only value that's high is out here, that's 0.33. And that is the kind of value on which you might not be able to reject the null hypothesis or reject the idea that the coefficient of D is actually indistinguishable from 0. The null hypothesis that is that this estimate, this parameter could actually be equal to 0. Going in line with the idea of confidence interval, so you also get confidence bounds. So this is the lower 95th percent confidence bound, the upper 95th percent. And if you had mentioned values different in the original pop-up screen saying I want something more than 95%, you would have gotten the 95% bounds as well as those new numbers. But if you haven't, these numbers are just a repetition. Okay. The obviously noteworthy thing is that given that these are 95% confidence bounds, you can reason from inferential statistics that whenever the p-value is less than 0.05, or even actually technically less than 0.1 because it's a lower and upper confidence bound. If it's anywhere less than 0.1, you should have the lower and upper on either side of 0. So here the lower bound is 3.6 and the upper bound is 14, so it doesn't intersect 0. So whatever sign your coefficient is, your lower and upper bound is going to be on that side of 0. Obviously when a p-value is as high as something like 0.3, which means you potentially could not reject the null hypothesis, then you would have a lower bound that could be less than 0 and you will have an upper bound greater than 0, right? And that should make sense in terms of how we understand confidence bounds and p-values. Okay, so this gives you the inferential statistics or the background associated with having each term in the model. So in this model, which I'm just going to highlight with some color so it's clear to you, in this model that you have out here, you now know which terms could potentially go in and which terms could not. Okay, or which terms you can justify putting in there and which terms might just be a result of random noise. Now in addition to these individual statistic associated with each individual term, you also have an overall statistic that's being captured through this ANOVA. So I'll just give that a different color. So the idea with the ANOVA is that you're trying to see how much of the variation comes from the regression model, and this cell is the equivalent of the mean square between. I'm talking about D12. And you have cell D13, which is the idea of how much of the variation still exists even after you've fitted the regression model. And you use the same concept. So these two terms are kind of like your mean square between and mean square error. They are the equivalent from the ANOVA, the traditional ANOVA that we studied. And you can calculate an F statistics and get a p-value for the F statistic. And what that p-value says is overall as a model, never mind that you have these statistics associated with individual terms, but overall as a model, can I test the null hypothesis that the model explains some variation? or is the variation explained by the model um, equal to 0? So it should give you an idea of that. And in many instances, you're really looking to make sure that this value is as low as possible, and you want your R square and adjusted R square values to be as high as possible. Okay, so great. So we discussed how you can do a multiple regression in Excel, but at this point we're going to also go a little bit beyond a standard multiple regression. The software kind of allows you to do it conveniently, but you could also, for instance, perform a multiple regression by hand, right? And the way you would do that, and this is really useful, is because you might not want to do an ordinary least squares, and that's what we're going to show you, how you don't have to do ordinary least squares. Just to jog your memory, the idea of ordinary least squares was to say that I want to minimize the sum of the squared deviation of each point from the line as measured along the y-axis line. So I want to measure the square of the distance of each point from the fitted line. And the rationale for using the square was, of course, to say that that you might sometimes have a data point that's above the line, sometimes have a data point that's below the line, so you'll have positive and negative values, and you want to represent all deviations in the same light. You don't want the positive and negative values to cancel each other, and you just want to minimize deviation. So you said if I squared all those deviations and just minimize the sum of those squares, it's a sum of the squares because each data point deviates from the line by some amount, right? So you want to minimize the sum of the squared deviation of each data point from the line. So that's the core idea. And so now what you might want to do is, and doing that conception allowed for this very neat derivation, such that you had a closed form solution for beta naught and beta 1 and so on, and it's very easy to implement. But now we have computers that are reasonably fast, and you might not want to have these neat closed form solutions, but you might just be willing to take an Excel sheet and do the regression through some other metric that you want to minimize. So instead of minimizing the squared deviation of the data points from the line, you might just want to take the absolute deviation. What we mean by absolute deviation is if the data point is 7, and if the fitted line at that value of x predicts, say, 5, this difference between 7 and 5, I'm just going to take it as 2. I'm not going to think of it as positive or negative. So whether the data point itself is above the line or below the line, I'm just going to measure the magnitude of that deviation and put them all as positive values and minimize the sum of those. So whether you want to do that, or whether you want to say my particular problem, I want to penalize it by using cubes instead of squares, or cubes would not really work, but I want to use the 4th power or something like that. You can do it yourself, and so this is what I call as the do-it-yourself regression. And the idea here is that I've copy-pasted the same data out here in this sheet, and what I'm saying out here is that these are the coefficients. So this value at B3 is beta naught, this value at C3 is beta 1, and we can just seed those with some initial values. I'm just going to seed that with 0, 0.5. You want to start with some reasonable values, and let's just put some dummy numbers out here, and we'll put 0 here. So these are just some dummy numbers within reasonable range. And the idea is, when you do that, I ask the Excel sheet, what is my model predicting, right? So it's essentially like saying that if these were the betas, then what would my model predict for these inputs? So if these were my betas, I'm just going to repeat that. If everything in row 3 from B through F are my betas, then given the input which is starts at row 6 and goes on, but we'll take one sample input, which is shown in row 6 from C through F. Given these inputs, what would my model predict? And the math of that is fairly simple. It's just that it's just the math of beta naught plus beta 1 x1 plus beta 2 x2. So that's what I do. I say B3, which is nothing but beta naught, plus the sum product of the arrays in 3 and 6. And the word sum product is nothing but saying you give me two arrays, I'm going to pairwise multiply the terms and add them all together. So what it's doing is it's doing B3 plus C3 times C6, D3 plus D3 times D6, and so on all the way till the end. And that's what the model is predicting. Okay, so I have the actual value, which happens to be 21, and I have something that the model predicted, and from that I can very easily calculate the residual. So what's shown in I6 is nothing but the difference between the actual y and the predicted y. So we do that, and we could square it, or we can take the absolute value, which is what I'm interested in. And so I have a set of squared deviation and I have a set of absolute deviations. It looks like I'm in general chronically over predicting, but that's just because I've given dummy betas for now. And out here what I have in cell O3 is the sum of the absolutes, the residual sum of the absolutes, and in O2 I have the residual sum of squares. Now remember, in an ordinary least squares regression, what you have in O2 is what you're trying to minimize by changing the values in B3 through F3. So you want to change the values in B3 through F3 and minimize what you're getting in O2. But in our particular example, what I wanted to illustrate to you today, I want to try and minimize what I'm getting in O3. So the way I would do that is to again go to data and click on solver. Again, if you don't have it, it invariably means you just need to add it from add-ins. And I tell solver saying I want to set this objective, which is O3. I want to minimize it. So I can either maximize it or try to set it to a value, but I want to try and minimize it. And I want to do that by changing the cells in B3 through F3. Okay, and given the kind of optimization approach you're taking, you might have to either give some constraints, which just means giving it some lower bounds and upper bounds. So give it something fairly reasonable, which is what I've already done here. And the way you do that is just go click on add and then mention the cell and give it a lower bound and then give it an upper bound. And that's what I've done here. And you have a couple of different methods of solving this optimization problem. I choose the evolutionary one. You can play around with the others because I just feel like it takes time, but I know for a fact that it's a safe bet. It's not. It's in terms of computational time, it's obviously not going to be the most effective, but I'm more than happy to pay that price. This is not. This particular example is not too hard a problem to solve, and I just click on solve. And then, as you can see, right now Excel is doing the computation, so it takes a couple of minutes. And what we will do is we will come back to this Excel sheet and look at the results in a minute. Okay. Okay. So going back to the slide. So in today's class we've seen two demos. One is using Excel to perform the multiple regression, and the second one is just going beyond the ordinary least squares, where you might have some other objective function that you want to minimize, and you should be able to fairly easily do that in Excel by just doing it the way I have demonstrated. Now we come to our next topic, which is the whole idea of subset selections. And it goes back, and I think we have the Excel results, so maybe we'll just take a look at that. And it says, do you want to keep the solver solution? And I say yes, and this is it. So and if you notice, this is a little different from the output that you got. It's not the exact same output. Perhaps if you'd let the solver go on longer, it might have come up to something maybe more similar, maybe more superior. In either case, because these objective functions are different, you should expect different answers. And this is the linear equation that solver gave you if it wanted to minimize absolute deviation. Okay, so going back to our slide, yeah, um, we spoke about how if you in that regression analysis you saw, so obviously the do-it-yourself regression does not give you any inferential statistics, right? It just is a way of getting coefficients. Now this is the other important part: which terms do you leave in the model, which do you take out? And when looking at that, we looked at this fairly simple idea of measuring each individual term through the p-value of the t-statistic. Just to jog your memory, I'm talking about this output, and I'm talking about these p-values that you see in column E from 17 through 21. And you could have an idea saying anything below a certain value is acceptable, anything above a certain value is acceptable, and that would be the most simplistic way of doing it. But the problem becomes that, I mean, there you're using only inferential statistic to decide which gets included and which does not. And the idea is that sometimes having a certain term inside which might be statistically significant could affect other terms. So the other variables could also get affected. So the problem is not, I mean, you could use inferential statistics and make a one-time decision, but what happens if you choose to add a variable and that changes the p-value of another variable? And also you might be of the opinion that what you care most about is your prediction accuracy, whether a term is significant or not. That you care about getting the best prediction accuracy, in which case it's still possible that adding certain terms is detrimental and removing them is might be the best. So oftentimes what we wind up doing is we wind up having some metric that measures how good we are performing as a model as a whole, not as the individual terms, right? And we already saw that. We, for instance, saw that in the ANOVA that we have. So this is measuring the model as a whole, right? And we might say all I care about is this p-value that you see in F12. That's all I care about. So can I make a decision on which terms should be in the model and which terms should not based on this one metric, right? You might have another metric which says I want to look at adjusted R square. We've not talked about that yet, but we will come back to that. But you could have this one metric that you want to minimize, and as we get more advanced, we'll realize how there are many other criteria which we could use to say what is a good regression and what is a better, and have a standard framework to compare two different models. Now, assume that you have the standard framework, or for instance assume that you care about F12 and you care about minimizing F12, which is the p-value associated with the F statistic associated with the whole model. Now it's perfectly possible that if you choose to add some terms that your overall model becomes better, and if you choose to remove some terms, so maybe if I removed D as an input variable as a whole, I might get a better p-value. Or it's also possible that if I added another variable E, it could be a lower p-value. But how do you go about searching through the entire possible set of input variables to figure out which ones should be in there and which ones should not? And this becomes a very important question, especially in light of what we've already discussed, which is prediction accuracy. I mean, so imagine a problem that you're faced with which has about 20 input variables and one output variable. Which subset of the 20, right? And I'm including that set which is all 20, and I'm including that set which is none of the 20, the null set. But which subset of that of those 20 variables should be there in the model, so as to give you the best performance, where performance is measured, for instance, through the p-value of the F statistics. Okay, that's one side of it. There's the other side also, which is that if you had a huge set of variables, sometimes the interpretation of the model might not be so clear, because these variables might be related to each other, and the coefficient that one of them takes up would compromise the coefficient that the other takes up, and so on. And it would be much easier, if you could interpret the model with just a smaller set of variables, at least the ones that are the strongest, and in some sense that enables you to get the big picture of the entire process. So what we're going to talk about now is that process of choosing that subset of variables, which is the best in terms of creating a model. The gold standard in doing that is this process called, let me just make that full screen. So the gold standard of doing that is this process called best subsets regression. Best subsets regression basically says, okay, so you have 20 variables, right? Or let's say I had 10 input variables. Let's try every subset of those 10 variables. So you'll start with having none of the variables, and then you'll have 10C1 combinations of having one variable, which essentially means having variable 1, variable, and that's one model. Having variable 2, that's one model. And then you'll move to the 2s, the 10C2 combination of 2 input variables are in the model. I have 1 and 2 in the model. I have 1 and 3 in the model. I have 2 and 3 in the model. I have 4 and 5. So all the combination of 2 variables. And then you'll have all the combinations of 3s. And you'll go all the way to having all the 10 variables in the model. Right? That's a lot. So that's 10C0 plus 10C1 plus 10C2 plus 10C3 combinations. But you know what? With good computational speed and a reasonably handleable problem, you might just be able to use a brute force approach and look at every subset that's possible, and you're done with it. So best subsets regression, often it's kind of seen as the gold standard of doing it, and it allows you to evaluate every subset. So it's essentially like creating that many different regressions. You possibly can't manually do it in Excel, but what you can do is you might be able to do it in another language. Like you might need a little bit of programming, or you might be able to do it in another software. But essentially that whole process of doing tools, data analysis, choosing regression, and getting that new output sheet, you would do that for various possible combinations of the input variables, for every possible subset of the input variable, and that's called best subset selection. Okay. Now, when that is not possible, right, we tend to go towards the sequential methods, and the problem with that is that there is a certain impact of adding and removing variables on each other. So I can never say that I'm going to add this variable and it's going to cause this effect, and then choose to remove another variable at a certain different point of time, but the effect of adding or removing a variable impacts other variables, and for that reason no form of a sequential approach is mathematically going to be exactly the same, be able to always recreate a best subset selection. But for the greater part, these methods that are sequential just work just fine. And in that light, I would say the more popular approaches are often called stepwise regression. You have forward stepwise selection, which means you kind of sequentially start adding individual variables to your model, and you keep adding till a point where the model does not improve any further. In fact, it gets worse, and then you take a step back and say this was the best state. You have backward stepwise selection, where you start with all 10 input variables in your model and you start sequentially removing them. Right? So for instance, one way to kind of show you how you could do that in Excel is to say, okay, so I had all A, B, C, D in the model. Now D is the worst. I'm going to remove that, and then say, does that improve my p-value of the F statistic in F12? So it would literally be like repeating the data analysis, going back to the data, going back to data analysis, saying I want to do a regression, but this time please do not include D in my range. So that's what I'm going to do. I'm going to include the label. Okay, so it's now I've done that, again, and now I have a different analysis, and lo and behold, this p-value is much lower than the p-value of the previous analysis. So maybe D should have been removed. And to kind of do this kind of a process sequentially removing variables and getting to the point where removing another variable is not a good thing, and you could use, for instance, the p-value of the individual variables to tell you in which order to remove the variables and so on. Now again, this is fine as long as you have a reasonable number of variables. If you have 50 and odd variables, it becomes very cumbersome. So you could just essentially use a software package to do the same thing, and we will briefly demo that. But before we do that, you finally have something called hybrid stepwise, which essentially is a combination of forwards and backwards stepwise. You start with nothing in your model and you sequentially keep adding terms, but at each state you see whether which term to add next or which term to delete next, and you put them on a common platter and make a decision on which to try. So that's hybrid stepwise, and what we're going to do now is demonstrate how you can actually do hybrid stepwise selection in Matlab. Okay. So this is a Matlab screen. If you haven't seen it, this is version R 2013b. The part that I'm selecting essentially is called a command window, and that's a place where you can just type instructions and get outputs, and we're primarily going to be dealing only with that space. So what I've done is I've already done this, but I'll just show you what I did, which is I just selected the data and I just copy pasted it in Matlab. So I just copied this, I went to Matlab and I said, oh, by the way, this variable y is equal to open square bracket, paste the data, close square bracket, enter. And Matlab has created a variable for me called y with that data. I did the same process for x, and all I'm going to do now is present Matlab with a simple command called stepwise. Okay, and I will give in x comma y. As if you noticed, it prompted me in terms of what to already put in there. But you can also provide Matlab saying I want some terms mandatory, they need to be in the model, and you can tell that, and you can also give a criteria for entering and removing terms. Just like, for instance, you could have used some criteria out here to look at these p-values to decide which order to go with. With Matlab, you can essentially say if it's below a certain range I want it to go, and if it's above a certain range I want it to come out. The default, I believe, is 0.05 and 0.1. But we're not going to give any of those terms. We're going to keep it simple and just hit enter. And what happens is Matlab looks at this data and it essentially comes up with an interface like this, and anything that's red basically means is not in the model. So right now there's nothing in the model, and this is the intercept, and there's no F statistic because there's nothing in the model and so on. But Matlab gives you a suggestion of what to do next. It says move x3 in. So all you'll do is you'll go to x3 and you'll click on it, and it's moved in. And immediately you notice that you have an F statistic, you have a p-value. It then says please move x1 in. So you'll go to the red dot and click on x1, and that's moved in. And it looks like the p-value went even lower. And then it says move x2 in, and you're still doing better. And now it says don't move any more terms in. Okay, so we went through a case where it sequentially said add A, add B, add C, and it smartly it said don't add anything more and don't do anything more. But you could see situations where it will ask you to then add something and then go back and delete something, but it kind of not only does it give you the interface to do it, so you could, for instance, add D and see what how the performance changes, and you can see the performance becomes worse, right, after adding D. So it's 1.76. If I take the D out again, the p-value is even lower. So essentially Matlab it allows you to do whatever you want, but it also gives you a recommendation by telling you what the next steps are. And at some point, if you say export, it will export the model for you, but you can also visually see it. It's basically saying this is the coefficient of x1, A, this is the coefficient of B, this is the coefficient of C, that you can see under the column coef, and it will also tell you what the intercept is, it will tell you what the R square is, it will tell you what the root mean squared error is, and so on. So it's a very convenient tool to play around with if you really had like lots of variables and you just wanted to play around more than do like a brute force approach to visually see what happens if you add one variable and remove a variable. This could be very convenient. Great. So with that, we conclude our lecture on kind of showing you how to perform a regression and interpreting results through software, as well as tackling the problem of variable selection or subset selection. Thank you.